Every time a new artificial intelligence model trains on billions of parameters, it generates an invisible byproduct: massive amounts of waste heat. Managing this energy has become the primary physical barrier to making these systems smarter. For decades, data centers relied on standard central processing units, or CPUs, which handled tasks sequentially and ran relatively cool. AI requires clusters of graphics processing units, or GPUs, working in massive parallel bursts that generate heat at a much higher intensity. This chart illustrates the resulting power density spike. A traditional CPU server rack draws about 5 to 10 kilowatts of power. An AI-optimized GPU rack consumes between 40 and 100 kilowatts, with nearly all that energy converting into heat. Keeping racks at that density from failing requires constant physical intervention. Facilities rely on massive air conditioning systems, complex liquid cooling loops, and technicians to manually replace hardware damaged by the thermal load. Advancing AI has become a thermodynamic gating problem. Land-based facilities are struggling to keep pace with the heat generated by these high-density architectures. To bypass the limits of terrestrial cooling, engineers are testing a radical alternative: physically relocating the backbone of the internet to the bottom of the ocean. The process involves packing high-density server racks into pressurized, watertight steel cylinders. These modules are then lowered by crane and submerged deep underwater. The deep ocean acts as an infinite, naturally cold heat sink. This provides continuous, passive cooling to the servers without consuming a single drop of municipal fresh water. There is also a strategic power advantage. By placing these modules directly next to offshore wind turbines, operators can bypass the congested terrestrial power grid and tap straight into localized, renewable electricity. The marine environment offers a dual solution to AI's physical limits: limitless thermal extraction and a direct connection to massive renewable power generation. Microsoft's Project Natick transitioned this idea from theory to the first major real-world proof of concept. It was designed as a research trial to test the long-term reliability of subsea hardware. Researchers sank a 12-rack module in the North Sea, powering the capsule with local renewable energy. Inside, the team replaced the oxygen with dry nitrogen, creating a sterile, non-corrosive environment for the electronics. This graph shows the primary finding after the 2-year trial. Compared to a duplicate control group of servers operating on land, the underwater hardware experienced just 1/8 the failure rate. By locking the module away at the bottom of the sea, engineers eliminated the routine bumps and jostles caused by human technicians walking the aisles of a traditional data center. Natick proved that removing human interaction and corrosive oxygen makes high-density computing significantly more stable. That research trial has now escalated into live commercial infrastructure off the coast of Shanghai. In the Lingang special area, a 1.6 billion yuan, 24-megawatt facility is currently operating on the seafloor. It was built expressly to support large language models and intelligent computing clusters. The project integrates with existing power sources, positioning the modules seamlessly between the phases of an active offshore wind farm. This commercial deployment reduces land use by over 90% and maintains a power usage effectiveness of 1.15, placing it among the most efficient facilities in the industry. Lingang proves that underwater data centers are now a viable, scalable blueprint for sustaining the next generation of AI growth. However, the ocean's cooling benefits come with unforgiving physical engineering realities. Maintaining these pods is a logistical nightmare. When a component fails, operators must deploy specialized, heavy-lift marine vessels to physically winch the massive steel cylinder to the surface for repairs. The hardware also faces relentless environmental threats. Pressure seals must withstand constant saltwater corrosion, and the outer hulls rapidly accumulate thick layers of barnacles, a process known as biofouling. There are also unresolved ecological questions. Biologists are still modeling the long-term impact of dissipating massive, concentrated amounts of industrial heat directly into local marine ecosystems. Sinking a data center swaps terrestrial grid issues for the hostility of the deep sea. The massive physical toll of AI remains. It is simply being managed through extreme marine engineering. As the computing demands of these AI models continue to scale, the tech industry's entire approach to infrastructure is being forced to adapt. The absolute limit on computing progress is no longer the speed of the silicon chips. It's access to raw natural resources like cold water and sustainable electricity. This shift is redrawing the map of the internet. Physical infrastructure is migrating away from inland populations to lock onto the Earth's natural cooling features and offshore energy corridors. Physical geography will determine the trajectory of machine intelligence. High-level code relies entirely on finding an environment capable of preventing a total thermal meltdown. Share this with someone who loves fun facts.
Share this with someone who loves fun facts.